Today we are going to learn about PyTorch Autograd, advanced techniques for dynamic computation graphs. We'll explore how to implement and manipulate dynamic graphs for complex models, equipping you with skills to adapt neural networks to varying input sizes and structures.
Welcome to our exploration of PyTorch Autograd and the advanced techniques for leveraging dynamic computation graphs. In the world of machine learning, dynamic computation graphs are pivotal for adapting neural networks to varying input sizes and structures. Throughout this video, we will dive deep into understanding these graphs, why they're beneficial in PyTorch, and how they're implemented through Autograd. By the end, you'll be equipped to handle complex models and optimize them for real-world applications.
Dynamic computation graphs are a foundational concept in modern neural network architectures. Unlike static graphs, which are fixed and predefined, dynamic graphs are constructed on the fly during the execution of a forward pass. This flexibility allows models to adapt to varying input sizes and structures, a critical feature for tasks involving sequences or varying input dimensions. Dynamic graphs are particularly useful in scenarios where the model needs to be highly adaptable, such as real-time data processing or handling variable-length sequences in RNNs. Understanding how dynamic graphs differ from static ones is crucial for leveraging their advantages in designing flexible machine learning models.
The adoption of dynamic computation graphs in PyTorch offers multiple benefits that enhance both the development and deployment of neural networks. One of the primary advantages is increased model flexibility, allowing researchers and developers to rapidly iterate on model designs. This adaptability is crucial when dealing with diverse datasets, as models can adjust dynamically to the variability in data. Additionally, dynamic graphs allow for more efficient memory usage, as they allocate resources only when needed, which is particularly important for large models and datasets. The ability to construct graphs dynamically also simplifies the debugging process, as developers can inspect the computation flow in real time. Finally, dynamic graphs facilitate rapid prototyping, enabling quick testing of new ideas without the overhead of predefining the computation graph. Setting up dynamic graphs in PyTorch is seamlessly integrated with the Autograd library, which provides automatic differentiation for all operations on tensors. Autograd constructs dynamic computation graphs on the fly, capturing the operations performed on tensors and enabling automatic computation of gradients via backward passes. To create dynamic graphs, you simply need to design your model using PyTorch tensors and perform operations on these tensors as you would with regular Python variables. Autograd takes care of tracking the operations and creating the computation graph dynamically. When you perform a backward pass, Autograd computes gradients for all tensors involved, which are essential for updating model parameters during training. This process is efficient and requires minimal setup, making it easier for developers to focus on designing and optimizing their models. Implementing real-time graph manipulation in PyTorch involves handling inputs and model structures that change during runtime. This capability is crucial for environments where data and requirements can vary unexpectedly, such as in real-time applications and interactive systems. By leveraging dynamic computation graphs, models can adjust their architecture and computation flow based on the input they receive. This feature is particularly beneficial for applications that require live monitoring and updates, such as autonomous driving or adaptive learning systems. Real-time manipulation allows models to reconfigure themselves, ensuring optimal performance without the need for reinitialization. This adaptability not only enhances the model's ability to respond to changes but also improves the efficiency of resource usage, as computations are tailored to current needs. One of the significant challenges in neural network design is adapting models to handle variable input sizes, which is a common requirement in fields like natural language processing and computer vision. Dynamic computation graphs provide an elegant solution by allowing models to adjust their architecture based on input dimensions. This adaptability ensures model consistency and performance, regardless of the input size. For example, in sequence-based models like RNNs or LSTMs, dynamic graphs enable the model to process sequences of varying lengths without compromising on efficiency. Similarly, in image processing, models can dynamically adjust to different image resolutions, ensuring that the input data is adequately processed. Practical implementation of these solutions involves designing flexible neural network architectures that can adapt to changes in input size, often using padding or variable length input handling strategies.
Recurrent neural networks, RNNs, and long short-term memory networks, LSTMs, are powerful tools for sequence prediction tasks. Their ability to maintain information across sequence elements makes them ideal for tasks such as language modeling and time series prediction. Incorporating dynamic computation graphs into these models enhances their flexibility and performance, especially when dealing with sequences of varying lengths. By utilizing dynamic graphs, RNNs and LSTMs can adapt their state transitions based on the input sequence length, ensuring that all elements are appropriately processed. This capability is crucial for applications like speech recognition, where input length can vary significantly. Real-world examples include adaptive language models that adjust to sentence length and context, offering improved accuracy and efficiency.
Optimizing performance in neural networks with dynamic computation graphs involves employing techniques that leverage the flexibility and adaptability of these graphs. One key aspect is efficient resource management, ensuring that computations are only performed as needed, which reduces memory usage and computational overhead. Dynamic graphs allow for the selective execution of operations, optimizing the use of available resources and enhancing overall model performance. Developers can take advantage of this by designing models that dynamically adjust computation based on input characteristics, thus balancing flexibility and speed. Techniques such as lazy evaluation and on-demand computation are often employed to achieve these optimizations, ensuring that the model remains efficient while maintaining the adaptability offered by dynamic graphs. Dynamic computation graphs have found numerous applications across various industries, offering solutions to complex problems that require adaptability and real-time processing. In natural language processing, models like BERT and GPT leverage dynamic graphs to handle varying sentence structures and lengths, enabling advanced language understanding and generation. In the realm of autonomous vehicles, dynamic graphs are used to process sensor data with varying dimensions, crucial for real-time decision-making. Additionally, applications in healthcare, such as adaptive diagnostic models, showcase the flexibility and power of dynamic graphs in handling diverse patient data. These case studies highlight the success of dynamic graphs in real-world scenarios, providing valuable lessons for future developments. As technology continues to evolve, the prospects for dynamic computation graphs in AI and machine learning remain promising, paving the way for even more innovative applications.
As we conclude our exploration of PyTorch Autograd and dynamic computation graphs, it's clear that these concepts are vital for the future of machine learning. The flexibility and adaptability they offer are unmatched, allowing models to efficiently handle varying input sizes and complex data structures. Looking forward, dynamic computation graphs will continue to play a crucial role in advancing AI technologies, with potential applications expanding across industries. We encourage you to experiment with these techniques in your projects, leveraging the power of PyTorch to create innovative solutions. Thank you for joining us on this journey, and we look forward to seeing how you will apply these concepts in your work.